Understanding Shor's algorithm with a simple analogy. Imagine you are a master codebreaker in a world where messages are encrypted using incredibly large numbers. To decode these messages, you need to factorize these large numbers into their prime components, a task that is nearly impossible with classical methods for very large numbers. Shor's algorithm, designed for quantum computers, provides a way to factorize these numbers efficiently, revolutionizing the field of cryptography. The components. 1. The encrypted message. This represents the number you need to factorize. In our analogy, think of it as a locked treasure chest. Treasure 2. The prime factors. Black key. These are the keys to unlocking the treasure chest, representing the prime numbers that multiply together to form the large number. 3. Quantum computer. This is like a super advanced code-breaking machine that can perform incredibly complex calculations much faster than any classical computer. The process. Let's break down the steps of Shor's algorithm using our codebreaker analogy. 1. Superposition and quantum states. Imagine your code-breaking machine can try all possible keys, prime factors, at once. This is because a quantum computer can exist in multiple states simultaneously, thanks to superposition. 2. Quantum Fourier transform, QFT. Your machine uses a special tool called the quantum Fourier transform. Think of it as a magnifying glass that reveals patterns and periodicities in the large number, helping you identify potential keys. 3. Finding the period. The key to cracking the code lies in finding the period of a specific mathematical function related to the large number. This function helps you determine the repeating cycles or patterns within the number. Your machine, using the QFT, identifies this period efficiently. 4. Classical computation. Once the period is found, your machine switches to classical computation to process this information and identify the correct keys, prime factors. This involves some additional calculations, but the hard part of finding the period has been handled by the quantum part. 5. Extracting the prime factors. With the period information, your machine can now deduce the prime factors of the large number, effectively finding the keys to unlock the treasure chest. Why it's complex? Shor's algorithm is complex because it combines the principles of quantum mechanics with advanced mathematical concepts. The quantum Fourier transform, in particular, is a sophisticated tool that allows the algorithm to find the period of a function efficiently, something that classical algorithms struggle with for large numbers. Impact on cryptography. The significance of Shor's algorithm lies in its ability to factorize large numbers exponentially faster than classical methods. Many encryption systems, such as RSA, rely on the difficulty of factorizing large numbers for security. Shor's algorithm poses a potential threat to these systems, highlighting the need for new cryptographic methods in the era of quantum computing. In summary, Shor's algorithm is like having a master codebreaker with a super advanced machine that can unlock encrypted messages by efficiently finding the prime factors of large numbers. By leveraging the principles of superposition and the quantum Fourier transform, this quantum algorithm can solve problems that are virtually impossible for classical computers, revolutionizing fields like cryptography. Understanding the quantum Fourier transform, QFT, with a simple analogy. Imagine you are at a grand concert hall where a symphony orchestra is playing a beautiful, complex piece of music. The music consists of multiple instruments playing together, creating rich harmonies and rhythms. Now, you want to understand the contribution of each instrument to the overall music. The quantum Fourier transform, QFT, in quantum computing is somewhat like this process of breaking down the complex symphony into its individual notes and harmonies. The components. 1. The symphony. This represents the complex quantum state you want to analyze. Just like a symphony is made up of many notes played by different instruments, a quantum state is made up of multiple amplitudes and phases. 2. The instruments. These represent the individual frequency components of the quantum state. Each instrument corresponds to a different frequency. 3. The music analyzer. This is your QFT, a powerful tool that can decompose the symphony into its individual notes, allowing you to see the contribution of each instrument. The process. Let's break down the steps of the quantum Fourier transform using our concert hall analogy. 1. The symphony begins. Imagine you are standing in the concert hall, listening to the symphony. The music is rich and complex, just like a quantum state that consists of various amplitudes and phases. 2. Applying the QFT. You have a special device, the QFT, that can listen to the entire symphony and analyze it. This device can transform the music from its time domain, how it sounds over time, to its frequency domain, the individual notes and harmonies. 3. Decomposing the symphony. The QFT works by applying a series of mathematical operations to the quantum state, similar to how the device in our analogy breaks down the music into its constituent frequencies. This process reveals the hidden structure of the quantum state, showing which frequencies, instruments, are contributing to the overall music. Understanding the output. After the QFT is applied, you get a new representation of the quantum state where each component is now expressed in terms of its frequency. This is like seeing the music sheet with all the individual notes and knowing exactly which instrument played each note. Why it's powerful. The quantum Fourier transform is powerful because it allows you to see the structure of a quantum state in a way that is not possible with classical methods. It can reveal periodicities and hidden patterns within the state, which is crucial for many quantum algorithms, including Shor's algorithm for factoring large numbers. In summary, the quantum Fourier transform is like having a sophisticated music analyzer in a concert hall that can decompose a complex symphony into its individual notes and harmonies. By transforming the quantum state from the time domain to the frequency domain, the QFT reveals the underlying structure and frequencies, making it a powerful tool for analyzing and processing quantum information. Understanding Grover's algorithm with a simple analogy. Imagine you are in a huge library with millions of books, and you need to find one specific book. The problem is that you don't know where the book is located, and the books are not organized in any particular order. In a classical scenario, you would have to check each book one by one, which could take a very long time. Grover's algorithm, designed for quantum computers, provides a much faster way to find that specific book. The Compo 1, the library. This represents the unsorted database of items you need to search through. 2, the book. This is the specific item or solution you are looking for. 3, quantum computer. This is like a super smart librarian with special powers that can help you find the book much faster than traditional methods. The process. Let's break down the steps of Grover's algorithm using our library analogy. 1, superposition. Imagine that your quantum librarian has the ability to look at all the books simultaneously. This is because quantum computers can exist in multiple states at once, thanks to the principle of superposition. 2, oracle function. The librarian has a magical device, oracle, that can check if a particular book is the one you're looking for. When it finds the correct book, it marks it in a special way. 3, amplitude amplification. After the oracle marks the correct book, the librarian performs a special trick, amplitude amplification, to make the correct book stand out more from the rest. This trick involves a series of reflections that increase the probability of selecting the correct book. 4, repeating the process. The librarian repeats the oracle check and the amplitude amplification a certain number of times. Each repetition makes the correct book stand out even more. 5, measurement. Finally, the librarian looks at the books, and the correct book, which now stands out the most due to the amplification process, is identified. Why it's efficient. Grover's algorithm is efficient because it reduces the number of steps needed to find the correct item. In a classical search, you might need to check each book one by one, which takes n time for n items. Grover's algorithm, however, can find the item in roughly n steps, which is significantly faster, especially for large data sets. In summary, Grover's algorithm is like having a super smart librarian in a vast library who can magically check all books at once and amplify the prominence of the correct book, allowing you to find it much faster than by traditional methods. This quantum algorithm leverages the principles of superposition and amplitude amplification to solve search problems efficiently, making it a powerful tool as quantum computing becomes more common. Understanding the quicksort algorithm with a simple analogy. Imagine you are hosting a party and you have a large stack of guest name cards that you want to arrange alphabetically on a table. Sorting these name cards quickly and efficiently is similar to what the quicksort algorithm does with data. The components. 1. The stack of cards. This represents the list or array of items, e.g., numbers, names that you want to sort. 2. The table. This is the workspace where you will organize the cards. The process. Let's break down the steps of the quicksort algorithm using our party analogy. 1. Choosing a pivot. Imagine you pick one card from the stack at random. This card is your pivot. The pivot helps you organize the other cards relative to it. 2. Partitioning. You now go through the remaining cards, comparing each one to the pivot. Place the cards that come before the pivot alphabetically in a pile to the left. Place the cards that come after the pivot alphabetically in a pile to the right. 3. Sorting the piles. Now you have 3 groups: cards before the pivot itself, and cards after the pivot. You repeat the same process for each of the 2 piles, left and right, choosing new pivots for each pile and partitioning them again into smaller piles. 4. Repeating the process. This process continues recursively for each new pile, sorting the cards into smaller and smaller groups until each pile contains only one card or is already sorted. 5. Combining the sorted piles. Once all the piles are sorted, you combine them back together. First, the left pile, then the pivot, and finally the right pile. You end up with a fully sorted stack of cards. Why it's efficient. Quicksort is efficient because it systematically breaks down the sorting problem into smaller parts, sorts them individually, and then combines them back together. By choosing pivots and partitioning, it significantly reduces the number of comparisons needed compared to simpler sorting methods. In summary, the quicksort algorithm is like organizing a stack of guest name cards for a party. By choosing a card as a pivot and sorting the other cards into piles before and after it, you quickly narrow down the sorting task into smaller, more manageable parts. This method allows you to efficiently sort a large number of items, making quicksort a powerful tool for app development when handling large data sets. Understanding the traveling salesman problem, P, with a simple analogy. Imagine you're a traveling salesperson. You need to visit several cities to sell your products, but you want to do it in the most efficient way possible. The challenge is to find the shortest route that allows you to visit each city exactly once and then return to your starting city. This is known as the traveling salesman problem, P. The components. 1. Cities. These represent the destinations you need to visit. 2. Roads. These are the paths between the cities, each with a specific distance. 3. The route. This is the path you need to find, starting from your home city, visiting each city once, and returning to your home city. 4. The problem. The main challenge of the TSP is to determine the shortest possible route that covers all the cities exactly once and returns to the starting point. The number of possible routes increases dramatically with the number of cities, making it a very complex problem to solve. The process. Let's break down the steps of solving the TSP using our salesperson analogy. 1. Starting point. You start at your home city. 2. List of cities. You have a list of all the cities you need to visit. 3. Possible routes. There are numerous ways to arrange your visits to the cities. For example, if there are only 4 cities, A, B, C, D, the possible routes are A, B, C, D, A, B, D, C, A, C, B, A, and so on. 4. Calculating distances. For each possible route, you calculate the total distance traveled. This involves adding up the distances between each pair of consecutive cities in the route. 5. Finding the shortest route. After calculating the distances for all possible routes, you compare them to find the shortest one. Why it's complex. The complexity of the TSP arises because the number of possible routes grows factorially with the number of cities. For n cities, there are n-1 possible routes. This means that even with a relatively small number of cities, the number of possible routes can be enormous. Simplified solutions. Since checking all possible routes becomes impractical with more cities, there are various approaches to find a near-optimal solution more efficiently. 1. Heuristics. Methods that quickly find a good enough solution without guaranteeing it's the best. For example, nearest neighbor. Always travel to the closest city that hasn't been visited yet. Greedy approach. Make the locally optimal choice at each step with the hope of finding a global optimum. 2. Dynamic programming. Breaking the problem down into smaller subproblems and solving each one only once, storing the results for future use. This approach can significantly reduce the number of calculations needed. 3. Genetic algorithms. Mimicking the process of natural selection to evolve better solutions over time. Starting with a population of possible routes, routes are combined and mutated to produce new routes, selecting the shortest ones for the next generation. 4. Simulated annealing. A probabilistic technique that explores different routes, occasionally allowing for worse routes to escape local minima, gradually focusing on shorter routes over time. In summary, the traveling salesman problem is like a challenging puzzle for a salesperson trying to find the shortest route through multiple cities. Due to the vast number of possible routes, finding the absolute shortest path is complex and computationally expensive. Instead, various strategies like heuristics, dynamic programming, genetic algorithms, and simulated annealing are used to find good enough solutions efficiently. Understanding the A-star search algorithm with a simple analogy. Imagine you are in a large park and you want to find the shortest path from your current location to a beautiful fountain. The park is filled with paths, some of which are straightforward while others might lead you in circles or dead ends. You have a map, but it's not enough to just follow the paths. You want to be efficient and find the quickest way to the fountain. The components. Sarsnan 1. The map. This represents the entire area you need to search. Think of it as the space where our algorithm will operate. 2. Your current location. This is the starting point. In our analogy, this is where you begin your journey. The fountain. This is the goal or the destination we want to reach. 4. Paths with distances. Each path has a distance, which represents the actual cost to travel from one point to another. 5. A guide with a special ability. You have a guide who can not only measure the exact distance you've traveled, but can also make educated guesses about how far you still have to go to reach the fountain. The process. Let's break down the steps of the A-search algorithm using our park analogy. 1. Starting point. You start at your current location. Your guide marks this spot as the beginning of your search. 2. Open list and closed list. Open list. This is like a to-do list. It keeps track of all the places you need to check. Closed list. This is like a done list. It keeps track of all the places you've already checked. 3. Evaluating paths. Your guide looks at all the possible paths from your current location and evaluates them. For each path, the guide considers two things. Actual distance traveled, G, how far you've walked so far. Estimated distance to the goal, H, an educated guess of how much further you need to go to reach the fountain. 4. Choosing the best path. The guide combines these two distances, G, H, to decide which path seems the most promising. This combination is called the F value. 5. Exploring the best path. The guide always picks the path with the lowest F value to explore next. This means choosing the path that seems to be the shortest overall to reach the fountain. 6. Updating lists. Once a path is explored, it's moved from the open list to do to the closed list, done. The new location at the end of the chosen path is added to the open list if it hasn't been explored yet. 7. Repeating the process. This process repeats, with the guide continually picking the most promising path and updating the lists until you reach the fountain. Why it's efficient. The A-star algorithm is efficient because it doesn't just follow a random path blindly. Instead, it makes smart choices by combining the known distance traveled and the estimated distance remaining. This way, it always aims to follow the shortest possible path, reducing wasted time and effort. In summary, the A-search algorithm is like having a super smart guide in a park who helps you find the quickest route to a fountain. By always considering both the distance you've traveled and the distance you have left, the guide ensures you reach your destination efficiently. This method of combining actual and estimated distances to make decisions is what makes ASA such a powerful and widely used algorithm in computer science.